Usually, when you think about a medical diagnosis, you expect this kind of engineering-level precision.
Right, yeah, like it's an absolute certainty.
Exactly. You break your arm, the X-ray shows a jagged white line, and the doctor points at the screen and says, there it is, broken.
It's super clean.
It's completely binary.
Yeah.
And, above all, it's incredibly comforting because we humans just love things to be visible and neatly categorized.
Oh, absolutely. We crave that structure.
We really do. Welcome to Kanerika's podcast, The Digital Shift. But when you step into the world of artificial intelligence, and specifically the raw data that feeds these massive systems, that metaphorical X-ray machine just shatters completely.
Yeah, it really does.
We are looking at a diagnostic landscape for predictive models that is entirely murky. Today, we're doing a deep dive into exactly why that is.
And, the gap between the clean, pristine data and artificial intelligence actually needs to function reliably, and the messy, chaotic data we can collect in the physical world is just a massive chasm.
A total chasm.
Models today are literally starving for quality data. And when they starve in the lab, well, they completely fail in production.
Which is the exact problem we're dissecting today.
Yeah.
If you are building, buying, or even just relying on predictive models in your business, you really need to understand how we bridge that chasm.
Because the stakes are enormous.
They really are. Consider Pfizer's recent machine learning initiative. They rolled out a deployment spanning 14 different projects.
14? Wow.
Yeah, 14. And by implementing the data strategies we're going to explore today, they are saving 16,000 hours of search time annually. Plus, they cut their infrastructure costs by 55%.
That is wild. Cutting infrastructure costs in half at enterprise scale is not some minor IT optimization.
Right.
It's a fundamental transformation of their operational economics.
Exactly. So, okay, let's unpack this. The mission of this deep dive is to really explore how data augmentation acts as an incredible shortcut to generalizing artificial intelligence.
Yeah, it's the engine behind that entire transformation.
We are going to explore its impact across various data types, from vision to text to pure mathematics, and we're going to do it by focusing on the why and the how, not just rattling off a list of technical jargon.
Thank goodness for that.
Right. We want to show you how manipulating the data you already possess is actually the ultimate key to unlocking algorithms that survive contact with the real world.
And to really understand the urgency here, you have to look at the timeline we are on. Gartner released this staggering projection recently.
Oh, yeah. I saw that.
They predict that by 2030, synthetic data, meaning data that is artificially generated or heavily augmented, will completely overtake real, organically collected data as the primary source for model training.
So wait, in just a few years, the vast majority of the experience a machine learning model possesses will be completely manufactured?
Basically, yeah, it will learn about the real world from an artificial one.
That is just crazy to think about.
Well, it's because the real world simply cannot keep up. Building diverse, manually labeled data sets at enterprise scale is brutally expensive, and often it's just impossible due to privacy constraints.
Right, the legal hurdles alone are huge.
Exactly. But the deeper issue is that real-world training data actually suffers from 3 fatal structural flaws.
Okay, let's break those down.
The first is insufficient volume. Like, if you feed a system a very small data set, it doesn't actually learn the underlying concepts, it just memorizes the specific examples you gave it.
Oh, I see. It's like a student who memorizes the exact answers to a practice test, but never actually bothers to learn the underlying math.
Yes.
The moment the final exam has slightly different numbers, they fail completely. Overfitting.
That is the perfect analogy. The model looks like an absolute genius in the testing lab and then immediately fails upon deployment.
Ouch. What's the second flaw?
The second fatal flaw is class imbalance. In reality, the most critical events you actually want to track are usually super rare. Take credit card fraud or a rare mechanical failure on its assembly line.
Right? Those don't happen every day.
Exactly. So if 99% of your data represents normal, healthy operations, the model quickly mathematically deduces something. It realizes the easiest way to achieve a 99% accuracy score is to simply predict normal every single time.
Wait, really? It just ignores the fraud entirely.
It literally optimizes itself to ignore the very rare events you built it to catch.
It games its own scoring system. That is wild.
Machines are very pragmatic. And the third flaw is distribution mismatch. We usually collect training data in these highly controlled, pristine conditions, like a studio environment.
But the real world is chaotic.
Exactly. If you train a computer vision model on perfectly lit, high-resolution photographs of license plates, It will completely fall apart the moment you deploy it to a grainy security camera in the middle of a rainstorm.
Because the distribution of the training environment doesn't match the deployment reality at all.
Precisely.
It makes me think of an aviation flight simulator. You don't wait for a Category 5 hurricane to physically manifest to teach a pilot how to navigate through one.
No, that would be terrible.
Right. You simulate the extreme wind shear, the failing engines, the blinding rain. You create those worst-case conditions artificially, so the pilot is prepared for literally anything.
Ah,
Data augmentation is effectively a flight simulator for artificial intelligence.
I love that. And that concept of simulation brings up a really critical distinction that trips up a lot of organizations. What's fascinating here is that we need to clearly separate data augmentation from data enhancement.
I hear those terms thrown around interchangeably constantly in tech spaces. It drives me crazy.
Me too, because they serve totally different mechanical purposes. Data enhancement is simply filling in the blanks.
Like completing a puzzle.
Right. If you have a customer profile missing a zip code and you ping a third-party database to fill in that zip code, you just enhance the record. You still only have one customer profile. It is just more complete.
So what's augmentation then?
Data augmentation is about mathematically multiplying and modifying existing data to actually expand diversity. If you take one single image of a dog and you rotate it 15 degrees, crop the background, and artificially lower the contrast, you just created 3 brand new inputs.
Oh, I get it. The computer treats those as entirely distinct experiences.
Exactly. You are actively expanding the boundaries of the data set.
That makes perfect sense, because the raw data we collect is fundamentally flawed. Too small, too imbalanced, too pristine. We have to actively distort it.
We have to mess it up a bit, yeah.
But let's move beyond just rotating pictures of dogs. It makes sense that we can trick a model with visual inputs because humans perceive geometry naturally. How does this manipulation actually work under the hood across different formats?
So in computer vision, the techniques are incredibly sophisticated. We use geometric transforms, sure, but we also use techniques like mixup. Yeah. This is where you take 2 completely different images and mathematically blend their pixel values together linearly. Or another one called cut mix, where you digitally cut out a rectangular patch of one image and paste it directly over another.
Okay, wait. If I blend a picture of a cat and a picture of a bicycle together into this semi-transparent mess, how does that possibly help the machine learn? Doesn't that just create confusing garbage?
It sounds totally counterintuitive, I know, but it solves a massive problem. If you only show a model-perfect images, it gets lazy.
Lazy how?
It just looks for one specific feature, like the shape of a wheel, and ignores everything else. By blending a bicycle and a cat, you force the algorithm's internal pathways to reason about a chaotic mixture of features.
Oh, interesting.
It teaches the system to identify underlying textures and edges even when they're heavily obscured or overlapping, which, again, is exactly how the real world actually looks.
That makes sense. That forces the model to work harder to find the signal in the noise.
And I imagine audio augmentation follows a similar logic.
Very similar, yes. Like you're injecting background static or utilizing time stretching, altering the playback speed of a voice without actually changing the pitch. You're training the voice assistant on your phone to understand you whether you're whispering in a quiet room or shouting over a passing ambulance.
You are intentionally building robust, battle-tested pathways. But, moving into text, specifically natural language processing, the mechanics have to change completely.
Yeah, this is where I really struggle with the concept. With a photograph, if I lower the brightness by 20%, the image is darker, but it's undeniably still a picture of a dog.
Right.
But in text, changing a single word entirely flips the meaning of the data. If I take the sentence, "The service was incredibly good," and swap good for bad, the sentence remains grammatically flawless, but I have entirely destroyed the sentiment.
You pinpointed the core fragility of text augmentation right there. Small perturbations can completely shatter semantic validity.
So what do you do?
Well, you can't just apply random noise to a paragraph. So we utilize highly targeted synonym replacement. Or, my personal favorite, back translation.
Oh, how does that work?
You take an English sentence, translate it algorithmically into French, and then translate that French output back into English. It almost always returns with slightly different phrasing, perhaps varying the syntax, but the core intent remains perfectly intact.
Oh, that's brilliant. It's like a highly productive automated game of telephone.
Exactly. And to execute this safely at scale without corrupting the meaning, we rely on advanced pre-trained language models, specifically massive architectures like bidirectional encoder representations from transformers.
Okay, bidirectional encoder representations from transformers. Aside from being a massive mouthful, how does a transformer actually know which words are safe to swap without breaking the sentence?
The magic is really in the word bidirectional. Older algorithms just read a sentence left to right, guessing what comes next.
Like predictive text on a phone.
Exactly. But this architecture evaluates the entire context of a sentence, simultaneously reading forwards and backwards, to deeply understand the specific context of a single word before it suggests any substitution.
Oh, wow.
It ensures the semantic meaning of the original label is preserved, because if you lose label integrity, your training signal just becomes poison.
It makes sense that we can manipulate images and text because those are human languages. But what happens when the data is purely mathematical?
That's a whole different beast.
Right, like if we're looking at a massive tabular spreadsheet of financial transactions, you can't just blur a decimal point. One wrong number destroys the entire logic of the ledger.
Yeah, tabular data is incredibly rigid because you have to respect the deep statistical correlations between dozens of different columns. You can't just randomly change a user's age without also checking if their income logically aligns with that change.
That would just create impossible people.
Exactly. But to solve that class imbalance problem we discussed earlier, where credit card fraud is dangerously rare, we utilize the synthetic minority oversampling technique.
Okay, break down the mechanics of the synthetic minority oversampling technique for us. If I only have, say, 5 examples of fraud, and I can't just copy and paste them, how does it mathematically invent a new one?
So instead of duplicating existing data, which just causes that overfitting problem, this technique plots your rare fraud events in a high-dimensional mathematical space.
Right.
It then draws an invisible line connecting 2 similar fraud events and interpolates between them. It mathematically calculates a brand new synthetic data point that sits directly on that line.
Wow.
It creates a wholly unique, realistic example of fraud that helps the model learn the precise boundary between a legitimate purchase and a stolen fund.
It's literally triangulating a new reality based on the coordinates of the old one.
That's exactly what it's doing. We also apply Gaussian noise to continuous variable.
That's Gaussian noise.
It's essentially a mathematical fuzz, a tiny bit of randomized variation added to a number. If a sensor reads exactly 4.0 degrees 1,000 times, the model might break if it suddenly reads 4.01 in the real world.
Because it's never seen it before.
Right. Adding that tiny bell curve of variation softens the rigid boundaries of the spreadsheet so the model isn't so brittle.
That makes total sense. And what if time is a factor? With time series data like stock market trends or predictive maintenance sensors on a factory floor, you can't just shuffle the timeline. The sequence of events is the entire point.
Yeah, for time series, you preserve the temporal structure using window slicing.
Window slicing.
You extract small subsequences from a massive timeline, forcing the model to recognize a pattern, whether it happens on a Tuesday or a Friday. Or we use time warping, which slightly stretches or compresses the timeline itself, simulating the exact same mechanical failure happening just a little bit faster or a little bit slower.
Now, running all these geometric interpolations and bidirectional translations requires massive computing power. I mean, if you were prepping a data set of 10 million rows, there has to be a structural bottleneck. Let's talk about offline versus online computation, because that really dictates how this is actually built in the real world.
Okay, so offline augmentation is like doing all your meal prep on a Sunday.
Right. You take your original data set, run every single transformation, save all those thousands of new variations as brand new files on a server, and then feed them to the model later. It saves computing power during the actual training phase, but it requires a staggering amount of physical storage space.
Because you just turn 10 gigabytes of data into 200 gigabytes.
Exactly. Online augmentation, on the other hand, is the equivalent of a short-order cook making a customized meal fresh to order. It happens mid-training.
On the fly.
On the fly. The model takes a batch of original data, applies fresh randomized transformations in memory right at that exact millisecond, learns from it, and instantly discards the variation.
So no new files are saved.
No new files are permanently saved to a hard drive. It requires immense continuous processing power during training, but it provides infinite diversity because every single time the model sees the data, it gets a freshly randomized version. If you're a business leader listening to this right now, you might be thinking, this sounds incredibly powerful, but how do I actually build this infrastructure without completely crashing my company's servers?
That is the big question.
And that is the exact industry-wide chaos we see every day. And it's precisely why we at Kanerika engineered a completely different approach. We orchestrate this entire process through our Flip platform. And I mean flip. Literally, it flips the traditional computing bottleneck on its head.
It really does.
The Flip platform orchestrates all of this data pre-processing natively on Azure. This makes it infinitely easier to prepare incredibly clean, structured data sets before any of these heavy, complex augmentations are even applied.
Because frankly, if your foundational architecture is messy, applying advanced augmentation just scales up your mess exponentially.
Which is why we at Kanerika also integrate Carl into this pipeline. Carl is our proprietary data insights agent. He constantly scans the raw data streams, spotting structural anomalies and statistical gaps in real time before the augmentation process even begins.
And the reason enterprise-grade infrastructure like the Flip platform is non-negotiable today is because of the sheer scale of modern algorithms. We aren't talking about simple linear regression anymore. We are dealing with massive deep learning architectures like generative adversarial networks.
Oh, generative adversarial networks. From a mechanical standpoint, these aren't just copying data. They are essentially fighting each other to invent it, correct?
Yeah.
It's like an art forger and an art detective locked in a room together.
That is the absolute perfect way to visualize it. One half of the network, the generator, tries to paint a fake synthetic data point. The other half, the discriminator, acts as the detective, analyzing the data to spot the forgery.
And they just go back and forth.
They compete millions of times, back and forth, until the forgery becomes so mathematically perfect that even the detective is fooled. That is how you generate hyper-realistic synthetic data.
That is amazing.
But these models possess millions, sometimes billions, of parameters. If your infrastructure cannot pump a constantly varying, massively augmented diet of data into those models fast enough, those billions of parameters will just memorize your data set instead of learning.
Right. And when you combine the correct augmentation strategy with the infrastructure that can actually handle it, the real-world implications are staggering. We're not talking about moving a decimal point on a quarterly reporting.
No, the impact is huge.
In our own deployments at Kanerika, we've seen a 50% faster time to market for fintech and health tech applications because these companies are no longer waiting months to manually collect rare edge case data. We've seen a 28% boost in retail customer retention simply because the predictive models finally understand the nuance of varied consumer behaviors.
Those are massive leaps.
And in global logistics operations, we are seeing an average of $1.2 million saved purely through optimized augmented forecasting.
You are fundamentally changing the unit economics of AI development at that point. You are achieving higher resilience and faster deployment without the prohibitive slow cost of manual human data collection.
But, and in technology, there is always a but. While the return on investment is massive, scaling synthetic pipelines introduces some incredibly dangerous failure points. If you misconfigure an augmentation pipeline, it doesn't just glitch, it catastrophically corrupts the system.
Oh, definitely. It's risky.
So what are the specific traps that destroy these models?
Well, the most immediate danger is label integrity errors. This happens when you apply a transformation that fundamentally changes what the data represents, but you fail to update the label attached to it. You are actively feeding the model a contradiction.
Okay, here's where it gets really interesting. Think about a directional road sign for a self-driving car. If you have an image of a sign pointing left, and your automated pipeline randomly flips that image horizontally to create a new visual variation, the arrow in the image now clearly points right.
Right.
But the text label in the computer's memory still says left.
Exactly. You have just silently poisoned the training well. The model is now hard-coding a mathematical rule that a right-pointing geometry means left. And the truly terrifying part of label integrity errors is that your training dashboard might still show your accuracy metrics improving, all while the model is confidently learning completely incorrect associations.
It is learning how to be confidently wrong.
Yeah.
Which is the worst kind of wrong. What is the next trap?
Bias amplification. We established that augmentation mathematically expands your data set. If your original, organically collected data is structurally skewed, say it overrepresents a specific geographic region, or only includes daytime photography, augmenting that data does not miraculously fix the skew.
It just makes it bigger.
You are simply calculating millions of new examples of that exact same bias.
So you don't solve the problem, you just build a louder, faster, more mathematically confident echo chamber.
Precisely. And in the realm of text, we face the risk of semantic drift. Remember our back translation example, the automated game of telephone? If you run a customer service complaint through translation algorithms too many times, the core intent can subtly drift away from the original meaning. If you are building an intent classification model to route urgent technical support tickets, a slight phrasing shift during augmentation can push that synthetic sample into the general inquiry category.
Oh, I see.
If you do not institute human review thresholds on back-translated text, your model will eventually lose its grip on nuance.
Knowing the immense rewards and the very real risks, let's ground this in specific industries. Healthcare is an area where data is notoriously difficult to acquire.
Healthcare is perhaps the most urgent use case for these techniques. Highly annotated medical data sets, such as MRI scans identifying rare tumors, are incredibly expensive to source. You need board-certified specialists to manually label the pixel.
And the privacy laws are incredibly strict.
Exactly. Strict patient privacy regulations make pooling data between hospitals a legal nightmare. But by utilizing geometric rotation, elastic distortion, which actually simulates the natural morphing of biological tissue and intensity normalization, a hospital can take a very small, legally compliant dataset of 50 tumor images and mathematically expand it into 10,000 distinct variations.
Wow.
It overcomes the scarcity barrier and the privacy barrier simultaneously, training a clinical-grade diagnostic model without ever exposing new patient data.
That is incredible. The autonomous vehicle industry operates on a similar principle too, relying heavily on that flight simulator concept we discussed earlier.
A self-driving car's perception model must understand how to navigate ultra-rare weather anomalies, like a sudden blizzard occurring at sunset while the vehicle has a mud-splattered camera lens.
You can't realistically dispatch a fleet of cars to drive around for millions of miles hoping to capture that exact dangerous scenario.
No, it's too dangerous and expensive. Augmentation, fused with full synthetic simulation, allows software engineers to instantly spin up thousands of geometric and visual edge case variations. The perception algorithms learn how to identify a pedestrian through a mud-splattered lens before the physical vehicle's tires ever touch a real highway.
Which brings us perfectly to the manufacturing sector, which is actually a brilliant showcase of how we at Kanerika apply this entire philosophy. We recently executed a project for a mid-size industrial manufacturer. They operated high-speed, high-volume production lines, but their quality control process was entirely manual, just rows of human inspectors physically checking parts.
And humans suffer from fatigue. They are inconsistent across different shifts, and they struggle to spot microscopic, low-visibility defects on fast-moving belts.
Exactly.
The structural challenge this client faced in automating this was that physical defect examples were incredibly rare. Their machines are highly efficient and mostly produced perfect products, which is fantastic for their quarterly revenue, but it is an absolute nightmare when you are trying to train an AI to spot flaws.
Because if you only possess 12 photographs of a microfractured gear, the AI cannot generalize what a microfracture looks like under the glare of factory lighting or on a slightly differently shaped gear.
So we at Kanerika architected a custom computer vision pipeline specifically targeting their bottleneck. We deployed a highly aggressive data augmentation strategy, we applied advanced geometric transforms, and we heavily utilized synthetic defect generation.
We basically made fake defects.
We artificially engineered highly realistic digital defects, scratches, dents, microscopic fractures, and mathematically grafted them onto images of pristine, perfect products. We created a massive simulated library of failure modes across every single production line configuration they operated.
And the operational results speak for themselves. Empowered by that synthetically augmented data set, we help their systems achieve over 99% defect detection accuracy across all configurations.
99% is huge.
Right, and the impact on their human workforce. We reduced their required manual inspection hours by 62% per shift, allowing them to reallocate those workers to much higher value tasks.
It perfectly illustrates how generating the exact data you do not possess is the key to solving a very real physical operational bottleneck.
So what does this all mean for you, the listener? When you aggregate everything we have explored today, from mix-up in vision to bidirectional encoder representations from transformers in text, to the mathematical blending of the synthetic minority oversampling technique, the through line is just undeniable.
It really is.
Data augmentation is not just an interesting theoretical trick for data scientists to play with in a sandbox. It is the core structural bridge between a fragile, overfit lab experiment and a reliable, production-ready enterprise tool.
It is the defining boundary between an artificial intelligence that works in theory and an artificial intelligence that actually survives in practice.
And that is exactly why we at Kanerika dedicate so much engineering focus to this layer of the stack. Our predictive deployments consistently achieve over 85% accuracy across diverse industries, and it's precisely because we master this delicate balance of data reality and mathematical simulation. We do not just feed raw data to models, we actively curate, augment, and heavily govern their diet so they are genuinely prepared for the unpredictable chaos of the real world.
And expanding on that chaos brings us to a fascinating, almost philosophical horizon. We began this discussion with Gartner's projection that by 2030, synthetic and augmented data will overtake real data.
Right, the tipping point where machines learn mostly from manufactured experiences.
If that timeline holds true, it forces a profound question about the year 2040. If tomorrow's models are trained entirely on the artificially augmented outputs generated by today's models, do we risk sealing ourselves inside a mathematical closed loop?
Oh, wow.
Without a continuous injection of messy, unpredictable human reality, does the system eventually just optimize itself into a corner?
That's a wild thought. The very chaos and messiness we are currently trying so desperately to mathematically smooth out might actually become the most valuable, highly sought-after commodity on the planet in a decade.
It really makes you wonder.
That is a paradigm-shifting thought to leave on. Thank you for joining us on this deep dive on the digital shift. Until next time, keep questioning your data, keep exploring the infrastructure, and we will see you on the next one.